for reliable performance. This introduces a challenge that compromises privacy. This talk today will cover three concepts, namely distributed optimization, DER prediction, and privacy preservation. State-of-the-art solutions as well as their theoretical properties will be discussed. And now I will share the bio for Dr. Annaswamy. Dr. Annaswamy is the founder and the director of the Adaptive Control Laboratory in the Department of Mechanical Engineering at MIT. Her research insights span adaptive control theory and its applications to aerospace, automotive, propulsion, and energy systems, as well as cyber-physical systems. She has received Best Paper Awards as well as Distinguished Member and Distinguished Lecturer Awards from the IEEE Control Systems Society and a Presidential Young Investigator Award from NSF. She is a fellow of IEEE and International Federation of Automatic Control. She is the recipient of Distinguished Alumni Award from Indian Institute of Science. Anu Annaswamy is the author of a graduate textbook on adaptive control, co-editor of 2 documents on smart grids, as well as 2 editions of the Impact of Control Technology report, and a co-author of a 2021 National Academy of Science Committee report on the future electric power in the United States. She served as the president of the CSS in 2020. She has been serving as a faculty lead in the electric power system workstream in the MIT Future Energy Systems Center since September 2021. So the talk today will be around 60 minutes long, including Q&A. During and after the talk, please feel free to send me your questions through the chat box. I think now, without further ado, let's welcome Dr. Annaswamy, and you can start, please.
All right. Thank you very much, Kyushi, for the very kind, gracious introduction. It's a pleasure to be with you all, and I look forward to sharing some of our results, as well as some points of view that I hope we will have a discussion on either during or following the talk. So obviously, things are changing significantly at the grid edge, since most of these changes are occurring at the distribution network. So let's take a closer look at what some of the changes are that are precipitated through this paradigm change. As you know, we are getting more and more eyes on the field. There is thanks to AMI, there's been a huge number of meters that were installed that gives us some window into what's happening at the grid edge. Because the conversation on on renewables is, of course, known to all of us. Not to belabor the point, but across the board, whether it's in New England or in Arizona or elsewhere, and not just in the United States, all around the globe, renewables are taking the whole scenario by storm, and that is also changing the conversation significantly. Moving forward, this not only means that we require more and more communication, that this communication is actually becoming very fine and heterogeneous and finely distributed in location as well, thanks to Internet of Things. And this not only allows us to have a window, but also communicate that information at requisite speeds. And so talking about speed, these timescales actually are becoming finer, not just because of the technology advances, but also because of the need associated with the dynamic signatures that are present typically in renewables. And that's also happening, again, as I mentioned before, because of the fact that these consumptions are not only do we have the ability to send that communication, but also that if you have demand response, where these loads are indeed flexible in one way or another and or curtailable or adjustable, then that technology advances allow us to basically communicate that over a range of fast timescales. So this means that we have the eyes on the field, we have the ability to communicate, we have the ability, and I haven't gone into the details of that in terms of the actuation with fast inverters, grid forming inverters, and so on. And so all of that says that resources are indeed available, and resource coordination is also a possibility. And the other thing that we need to understand is also that multiple stakeholders are present. So to get a sense of this distributed paradigm, as you all know, if you look at decision-making in power systems, the traditional thinking has been that, distribution system remains as an appendage, but much of the decision-making really happens between load serving entities and markets, and to manage the optimal power flow, which is then basically communicated to the transmission system, and those then basically are in turn stepped down all the way down through the distribution system to the consumer, and that sort of is basically how they all talk to each other. But obviously this picture is changing tremendously. As we pointed out, the renewables are entering the picture, which means how that interfaces with bulk generation, as well as the grid edge closer to the distribution system, has to be understood. Demand response is allowing consumers to participate more actively into the markets, and also provide they want to provide an opportunity to ensure that this distribution system also becomes active and becomes more efficient. So everywhere, wherever the demand responses, you could also think of storage as another asset that becomes available in time and varies with location. And all of the power electronics has to be there in order to provide this decision-making at the right time scale. Microgrids provide yet another microcosm of decision-making and way in which you can have a organized set of prosumers. And finally, the storage becomes more nuanced, especially with explosion of electric vehicles, with this whole paradigm of electrifying everything, which basically says there are tremendous amount of opportunities with storage on wheels, and you want to be able to integrate that as well. And so all of them essentially will have to come together and form a whole in here, right? So the point that I would like to really address in here is that when you have multiple stakeholders, these multiple stakeholders really come from different points or origins of ownership. And so not all of these are going to be utility owned. And so some of them are going to be private. And so those ownership boundaries then will have to be appropriately acknowledged and preserved. So the first set of points that I would like to present today is ways in which we can essentially leverage the presence of multiple stakeholders, carry out optimization in a distributed sense using the notion of proximity-based coordination. And the nice thing about it is not only that it allows us to carry out distributed optimization, but it basically provides a framework for preserving sensitive information, and therefore has a potential to lead to retail electricity markets and have a private exchange of sensitive information. Not only do we want to have the market structure be enabled, but distributed grid edge and with increased amount of renewables also propose other challenges. How do you, for all these injections that might occur across the board, as the penetration increases from 20 and 30 to 40, 50, 60 and above, you're going to really have issues of voltage control. And so how do you manage that? And obviously, one of the ways in which you can really address this issue of increased DER is through duck curve. Is it possible to manage that? And I would like to walk you through some of the results there. And as we talked about it, there's this explosion is also allowing us to leverage the increasing presence of IoT networks. And so here is where, if you really want to be able to understand demand response at its really extreme, if you will, in that all of the IoT devices basically are giving us an opportunity to provide additional assets, then we want to be able to predict what these assets are, and we want to be able to get that information without compromising basically the privacy of the individual owners. And so I'd like to walk you through a specific example of how this can happen and how, again, it can provide a specific grid service such as the load swing. And so the overall, all these points basically are allowing us to make use of efficient use, and not only that, judicious use of IoT networks. So let's start with the first one. So the point with the grid edge explosion is, again, been stated before. And so, if you were to look at this picture here, and with a distribution grid, so really we have a scenario where the primary feeders with the secondary feeders essentially allow us, and if you were to do the math in here, 200 times 400 times 1,000 really leads to a huge number of active assets. And so with these billions of nodes providing the opportunity in terms of power generation and consumption, the question is, can we then really understand, and this is the right place to the big data and analytics to figure out how this data can be efficiently managed. So the first point that I want to address is the scale. And so I want to walk you through a specific distributed optimization exercise that tells us that here is a way in which this big data could be managed in order to carry out one of the nerve centers of power systems, which is power balance and optimal power flow. So in order to do that, what do we have to do? Some sort of a cost function is being minimized, whether it's social welfare or losses or the number of critical loads that are picked up or what have you. All of them essentially provide you with some sort of an objective. And obviously you want to carry this objective out subject to real constraints in the grid. And so this is really the problem. So and this is something that we can do fairly in a straightforward manner at the bulk level, at the transmission level, but then as you start to move towards a distribution grid, it gets more challenging. And so how do you deal with it? How do you deal with the scale? And so the whole idea then would be to parallelize this so that you carry out the same problem. And so if I start with this optimization, can I come up with a number of distributed solvers so that instead of having 2 million nodes doing the central optimization problem, I basically distribute them over, so let's say, 1,000 of them. So each of those 1,000 nodes basically have an order, 3 orders of magnitude reduction in the complexity, and they're solving something that is deals with that dimension. And so in order to do that, the fundamental concept here is that you have to start to partition this problem. And when you partition this problem, obviously you have to partition it with respect to the primal variables as well as the dual variables. And so that's what these things are then saying. So what we are going to introduce is basically a copy of these primal variables. And every one of them basically is going to have the outside copy so that in the atomic space, you are able to, with these partitions of both the L and the O, you're able to deal with each of the optimization atomically in parallel with every atom basically marching forward. And so then you would have 2 things here, right? One is that you have a reduction in the space in the A's, which is great. So now you've come from 1 million to something of the order of 1,000 or even 100. Now, what you also have to do is to make sure that if you've got these copies, and the copies have to converge, and the copy convergence is the coordination constraint. This is an extra constraint now that I've introduced into the picture, right? So let me just walk you through a specific example to explain this point more clearly. So imagine now you have a very simple problem where the whole dimension of this dual the primal variable is just 4. But then these are coupled through these power balance constraints, let us say. And what really this says is that the atom 1 is connected with atom 2. Atom 3 and 4 are connected with atom 1. And then similarly, you've got atom 2 talking to atom 3 and 4. So for all of these things, then you can partition it using 3 atoms where you have a copy, for instance, in here, you have a copy of Y2, and therefore you have, this becomes its own individual standalone entity that will do its optimization. And this is what this will do as well. And so now you have these extra edges, and the copies will have to converge to the true value. And so, as I mentioned before, you've got these primal partitions and this constraint partitions. And here in this particular case, the partitions are basically coming because of this L1 and O1 indicated in here. And now you have an atomized decision variable, and the atomized, decision variable now is going to be 3 in number. And even though in the original space, it might be increased because I've reduced the complexity from 4 to 3, I now have, I have reduced that kind of complexity. And you can imagine I can do the same thing from 1 million to something that is significantly smaller. So if you now go into the details of the optimization itself, then you now have to worry about how quickly you can carry out the optimization. And so this is where the Lagrangian and the theoretical details of regularization come into the picture. So as you all know well, in order to make sure that, you come up with a solution to the problem, you set up the Lagrangian, but then in order to make sure that you really don't take very large step sizes and you converge fast, because it's very, very gradient steps, algorithms can be very slow, you introduce this additional component in here, and you basically adjust your primal variable and the dual variable like this. Now, in order to carry out that implementation, you have to make sure that when you indeed exchange information, you acknowledge the fact that this information is coming from disparate sources, and therefore you want to keep the sensitive information private. And this is where the specific proximal atomic coordination is very helpful, where we take these dual, the proximal terms, as I said before, is basically accommodated by this yellow term, but then the dual variables basically have this extra layer of defense, of privacy. And it is this that allows you to not really reveal sensitive information. And so the way we do that is basically by having the extra, something known as a predictor corrector step that introduces these new variables, mu hat and nu hat, and you're only exchanging the nu hat information, and that basically allows you to protect the privacy. So to just give you, and then of course, theoretically, we can show that this works very well, and indeed it converts to the optimal value. And the way in which the privacy really comes about is because at every iteration, the information that you exchange is basically given by what is indicated in these blue arrows. You have these primal variables, and the dual variables corresponds to nu hat. And so because we are not revealing the new information, which basically it represents like a shadow price, and describes a tension between meeting the local constraints versus the network constraints. And therefore, you're keeping the real value private. And so in comparison to, say, DADMM, then it is more privacy preserving, which gives you a very important protection of privacy. So what this does, it gives us an opportunity to go towards a retail market structure. So imagine now you have a scenario where indeed you have not lots of DERs, and these DERs are owned by multiple distinct disparate owners. So you could have a scenario where you have a primary feeder, and now that primary feeder, if you disaggregates into the secondary feeder, and each of those secondary feeder nodes disaggregates further into various devices where IoT devices are connected to some of these points. And some of them could be microgrids, some of them could be EV parks, and so on. And so now you have a scenario like this, then what you want to do is to basically have this multi-tier retail market where you have one market at the primary level, which basically has ultimately, say, for instance, a distribution system operator who might be sitting at the point of common coupling and managing, say, for instance, if this RM coordinator is sitting at a substation, this DSO could be a combination of different substations. And that all of that is happening at the primary market level, which could be electrically co-located with the primary feeder. We then have below that a secondary market where this secondary market basically operator corresponds to, say, for instance, node 90 in here. And that node 90 basically works with different, sorry, before I go in there, the different consumer market operators, say, for instance, this ICA IoT coordinated asset could represent this entire radial feeder. And this one, the second, another one could be the second one and so forth. And all of this is what could be presumably what is happening at the secondary market level. And then you could have a third one, which is much, much closer to the edge, which probably could be some sort of a for-profit kind of a setup with aggregators. And those aggregators basically represent the interests of these individual homeowners or EV charging stations. So now the point is that what this allows us to do is to basically utilize the PAC type of coordination, which preserves privacy at the primary market level. And it gives you an opportunity to basically have incentives in allowing these assets at the primary level to have a better response. For example, this particular exercise that we did, we got a scenario where this retail market that I showed you, we were able to carry out a use case study using the IEEE 123 feeder. And what we got was that these kinds of responses compared to, say, net metering or a traditional or a no export kind of scenario. For example, if you had flexible loads, what we found is that we were able to come up with a retail compensation for them to actually, let's say, for instance, provide an incentive for them to either adjust or curtail their loads. We got an opportunity to also show that the generators were not really getting overpaid or having no compensation, but a fair retail rate. And the even more interesting thing is in this particular study, we observed that the customers actually have a lower electricity rate, which in comparison with what could happen from some of the other things, and a lower revenue for the utility, which seems to suggest that. So the lower electricity rate was, say, for instance, it went down in our study from 11 cents to about 3 cents. And the lower revenue is actually consistent with the conversation that is ongoing in this scenario, which says that you're really moving away the business model wise from a commoditized market to a performance-based rate making. So, and we can actually go down further. If all of these things are happening at the primary level, if you were to now go into the secondary market level, you can actually use this privacy preserving algorithm and the structure to monitor exactly what their track record is, what kind of commitment scores can we come up with. If you have, let's say, for instance, these different consumer market operator that provide with a certain kind of commitment here. And what you see is the solid line, whereas the dashed line is the actual performance. And so I think I've indicated that here. So solid line is the schedule, whereas the dashed line is the actual. So that says then that at some points they really renege and they're not able to come through. So then we can accommodate that by basically monitoring what they're doing, and the commitment score drops, and that commitments whenever they don't really follow through. And we can use that commitment score to really keep an eye on how vulnerable or how reliable are these consumer market entities that are participating. And so it could be that they've installed a third-party device, which basically is exposed to some sort of attacks, or it could be that they're simply not able to come through with whatever they have preserved. So it also, this whole market structure gives us an opportunity to provide these kinds of additional state variables, if you will, especially as the number of DRs really explode. So the next point that I would like to make here is voltage control with the same kind of increased penetration of DER. So in order to do that, because we're looking at a distribution grid and because we want to accommodate unbalanced kind of architecture, we, instead of going for a branch flow type of model, we used a current injection type of model. And the current injection model basically gives us an opportunity to deal with the non-convexities in a better manner than the branch flow model could do. So specifically, what the nonlinearities, if you're going to represent all of the variables in here using current injections and use the network structure in order to really understand how all the intervariables are interrelated, keep in mind that the active and reactive part are going to have quadratic nonlinearities and non-convexities, even because of large angles. We want to make sure that we really create a convex-convex constraint. And the idea here basically is that when you have a conic, and that conic is embedded in a polytope, and each of the polytopes basically have linear boundaries, and those linear boundaries basically give us a way of improving the complexity of the problem and having a guaranteed solution. While it is true that we've increased the dimension because of this kind of an embedding, the nice thing about it is that because there are linear constraints and because we can introduce suitable pre-processing, we actually can implement this algorithm very well. So in fact, if you were to look at the complete current injection model with all of the different constraints that we have introduced, including voltage limits and current limits, and consider the problem of really having multi-phase grids, then you can show, and we've done a study where we've analyzed it for a whole bunch of networks, and we find that the optimality gap actually is as small as it is for nonlinear solvers. And in addition, the CI approach actually gives us much shorter runtimes. So with this kind of a CI model, we atomized it using the PAC algorithm that I mentioned to you before, where the coupling variables we're keeping in mind were the nodal voltages and the copies were for the downstream node voltage coupling. And we have to do the same thing even for the branch currents. And so with all these different copies that we did just, as I mentioned before, for the coordination constraints, and when we evaluated it on a 13 node network, we found that the feasibility constraint and the consistency constraint, which basically makes sure that first, the quality constraints are satisfied, and second, the copies are converging to the true value. It actually did it quite well. And here are is a more detailed comparison of the CI model with the branch flow model. And so, and indeed, there are very clear trade-offs that we can obtain. And the nice thing about it is that it gives you an opportunity to deal with the unbalanced flows in a much better manner. And so, like I said before, here are the feasibility metrics. And if you were to compare it with the BF model, we can actually get a more numerical precision with much lower amplitude oscillation. So while it's slower to converge, it actually converges to a much smaller error, which is an important advantage. So we took this and then we evaluated it for voltage control, and we really wanted to have compare it against realistic data. And the goal here, the cost function, was where you minimize the losses in some case. We also looked at voltage deviation in other cases, subject to three-phase power balance and with line losses. And we assumed that we're not doing this at a very fast time scale. So we assumed that whatever the set points are that we're providing for smart inverters and for demand response are all being followed. And so we considered different kinds of cases. One is where there are different loads and shunt capacitors, so that those are basically the switch settings, and that's the baseline case. We took that and then we evaluated it with demand response. We also evaluated with rooftop PVs. And then, of course, we considered a combination of all of them. And the kind of improvement that we got is apparent from these results in here, where you can see that this is basically phase A and B. And you can see that So for instance, these indices mean that there is a 37% of penetration of PV, and then we increase it further with the purple. So obviously you can see that the purple and the orange do much better than the other cases, which is also apparent from these figures here, which basically looks at what happens across all of the agents across a 5-minute time period. So without any kind of distributed control, obviously you have this steady decline. With the injections that we have coming from the demand response as well as PV, you can see that we do much better in terms of the overall voltage control. So, and this, you could look at the improvement in another way, which basically is the management of duck curves. And so we all know what this is. And so if you take the net load because of solar generation, as the sunset approaches, you really have to line up a whole number of generators, and the ramp rates become significantly more strenuous. And so how do you manage that? And so the steep ramping is really what you want to address. And so we evaluated what happens with our particular algorithm for this duck curve. And we considered in this particular case an IEEE 34 node, where we assumed that the PV units are basically providing variable power factor with 38% penetration. And we also assumed that there was flexible cooling loads, and we assumed that batteries were present in 3 of these nodes. And so with this kind of an approach, we compared 3 different categories. One is, and the distributed control used the PAC algorithm that I mentioned before with another variation. We wanted to really introduce an accelerated version of that, where you basically not only look at the current instant, but also the past. And so you use that information to further update both the primal variables and the dual variables. And what that does is also not only provides acceleration, but it also provides additional masking, not only for the dual variables, which the PAC algorithm already had, but even for the primal variables. And that's what's indicated in this purple window in here. And again, the model that we chose was the current injection model, so that we can have a three-phase unbalanced distribution grid in our study. And again, we did all of the linearization, as I mentioned before. And so the local control is the one, in terms of comparison, each DR manages its own loads and devices. There is no coordination between them, whereas the distributed control is the one where you have this extra coordination between these different agents. And the local control was basically trying to minimize the daily peak load, whereas the distributed control, we were minimizing the hour-to-hour demand at the point of primary coupling. And we used a multi-period approach with the rolling horizon in the whole overall algorithm. And this led to these results that you can see. So again, the blue is the baseline, where really there is no interaction and there are no batteries or flexible loads present. The local one is managing all of its stuff individually with no coordination. The distributed controller is doing the coordination using the PAC algorithm. So you can see that there's about 23% reduction in ramping. So again, what this says is that here is a way in which you can essentially leverage outside resources that may become increasingly available. And by having the appropriate structure, we can have, and the market structure to incentivize these assets to participate, you can essentially provide this kind of a grid service, which is improved voltage control. And in this particular case, what I'm trying to point out in here is also better management of the duck curve. So this is all like one set of results that I wanted to convey to you when it comes to managing the impact of increasing DERs on the grid by introducing some of these optimization constructs. So I want to now go on towards even closer to the IoT networks, closer to the consumer level, and really understand how we can leverage these IoT networks in order to really have improved grid performance. So the issue of privacy becomes more important as you go closer to the consumer level from the, let's say, from the substation level. And so obviously, if you want to have any kind of communication that is all, indicated in this figure and here across these different devices, we always have to worry about compromising, not compromising the privacy of the specific individuals. And this is where we found that a specific machine learning tool, which is federated learning, really becomes extremely useful. And I want to talk about how that can be, again, brought into the picture. So remember, we talked about the overall structure in here. You've got your primary feeder, your secondary feeder, and the consumers, and you've got each of the consumers have lots of IoT devices, and they've got all their data. So if you want to then have all of these consumers curtail their load and you want to participate in some sort of retail market, then you would have to send all that data right here, maybe to a centralized entity, or maybe all the way here. And when you send all the data, there is some sort of an aggregator sitting there, and then maybe even participates in, say, through the FERC 2x4 rule at the bulk hour market. But then that means that the consumer will have to reveal all their sensitive data, and that can really prevent them from participating in their assets, right? So this, here clearly I'm moving away from behind the meter type of discussion to a scenario where these consumers actually are participating actively in front of the meter and getting compensated for their performance instead of just basically some sort of a rebate program and from the utility. So how do you then not compromise privacy is the question. So this is where the notion of federated learning versus machine learning comes into the picture. So the whole concept of federated learning is basically to coordinate information and only share the information that is necessary. So instead of sending all of the house data directly and then taking all that and having a centralized entity carrying out some sort of a training of the neural network and then a prediction, which is really what you need to do in order to carry out this performance, you basically shift the boundary where you start to exchange information a little further down the line. So what this does is that it allows some of the computations that you have in here distributed across the house data, across the local entities and the global entity. And so what this federated learning allows you to do is to basically carry out a good bit of the computation which uses sensitive data in-house, and only transmit things that are most relevant and crucial to the global model. So this is basically the main idea of federated learning. So what this does is that, if you go into the details, then this you can find a lot of details in the IEEE IoT journal publication. And what this does is that, at the core of machine learning, let's say using a neural network, you have some sort of a gradient computation, right? And so the gradient computation in turn gives you an update of the weights. So what is being suggested in here is that there is this thing called federate, which is basically the computational entity associated with each of these IoT devices. And these federate basically does the computation of the gradient. So step number one would be that you basically have the weights coming from the global model to the federate. And the local federate uses the information that they have from the house data and then compute the gradient. And they only send the gradient to the house model. And because you're not using sensitive information and sending that itself all the way to the global model, you're essentially preserving privacy. And so then what the global model does is basically takes all of the gradients from all of these federates and does a weighted averaging and updates the weights. And then the whole process repeats, right? So you've got the global model sending the weights, and then there are all these computations, 2, 3, and 4 that are all being performed locally at the federate. And finally, the final step of the gradient is going back to the global model. And we repeat this process. And so that allows you to essentially have each gradient computed locally, and the local information could be based on a whole bunch of machine learning features that are all being computed internally. And that allows, again, accuracy and at the same time privacy preservation. So we implemented this in here again at this secondary, the local consumer market level. And what we did was to take 1,000 of these IoT devices, and we compared, we predicted what the consumption would be from each of these devices using this federated learning process. And what we observed was that our data, this is actually what you're seeing for one of those federates, and we compared the picked one at random and, providing you this comparison. And you can see over a 24-hour period, you can actually we get a very, very good comparison of the two. So we also did this comparison over 24 hours using Pecan Street data. And so as to really validate this with more accuracy. And you can see that our prediction, except for that we are under predicting the energy consumption in the evening, we actually do pretty well otherwise. We also used this machine learning based project prediction. So everything that I talked about in here was basically for predicting. So for example, sorry to go back here a little bit. So I am trying to predict. So what is this whole neural network trying to do? It's trying to predict what happens to the power consumption on, let's say, for instance, on a Tuesday at 10 o'clock. And so what we found was that what was really useful, a good feature set, was what happened 5 minutes ago, what happened 15 minutes ago, what happened a day ago, and what happened a week ago. And so that was an appropriate feature that we found was useful and gave us the most efficient type of prediction, because otherwise you can see that the accuracy is very good here compared to many other federated learning based papers. And the reason why we were able to do so well was because of careful selection in the feature set. And if we didn't have the right kind of support input vector into our neural network, and we found that it really was not providing accurate prediction. So, and this is also, again, substantiated in the Pecan Street data prediction that you're seeing. So the last thing that I would like to talk to you about is what we did with this prediction also. So not just, from the point of view of the performance metric of a prediction error, but also from the point of view of a particular grid service. And in this particular case, what we really evaluated in is using load swing. So the whole idea is that you have a particular prediction, right? You have a p hat. And now, so let's first do some definitions as to what would we mean. So let's say you were to take the actual data and you calculate delta p. And so you look at the 90th percentile of these variations, and that basically sets up the threshold. So the way we defined a load swing is if that the delta p at any time basically exceeds this 90th percentile threshold. And so we now have another metric, which is load swing. And so what you see here is again what we got by evaluating it for a 1,000 node IoT network, where we assumed that some of these IoT nodes came from home energy managers, and some of these IoT nodes came from EV charging stations. So it was a combination that it was 1,000 nodes. And again, we got grid lab data to see what a typical consumption pattern would be. And again, it was difficult for us to get actual data for independent houses. So we created this node synthetically by having one of the nodes corresponding to, or a few of them correspond to real data, and the other ones we basically perturbed it using a Gaussian distribution, and that's how we created the network. And again, this is something I hope we can have a conversation. And while it is true that in many, many cases, data seems to be readily available, in our case, we found that the data is not always the one that we're looking for, because we're looking for these kinds of specific things where, these are anonymized data typically, but from a whole slew of, let's say, buildings or from, so actually in this case, these were from buildings, sorry, not from EB. These are all from basically 1,000 buildings. So if indeed real data is available, it would help us sharpen our prediction, our tools much better. So we took this 1,000 node IoT network, we set up the threshold to be 31 kilowatts, and we evaluated the performance by actually not only using, looking at power swings, but actually introducing an algorithm for curtailing the loads. So let's assume that with this 1,000 node network and the threshold set to 31 kilowatts, that among these 1,000 nodes, some of them are curtailable. And so at all of these, which was a percentage. So the percent, we implemented then an algorithm with assuming the direct load control was indeed possible for these buildings, that whenever, so we looked at the prediction came from the federated learning based algorithm. And whenever the predicted load exceeded this threshold, the load was curtailed. And so we saw, this is the results that we got again for a 1,000 node simulation. This was one of the federates, and we evaluated what happens to that. So you can see that anytime, you can that the blue is the actual power swings, and the orange is after the peak shaving procedure, where you basically clip at any time the load swing occurs and it exceeds 31. So you can see across the board that for most of the cases, actually the swing reduction works quite well. So there are some occasional ones where the prediction is off, which is indicated by the negative points in there, because that's where we over predicted the power swing, and therefore that's the reason why the power swing is becoming negative. But those are fewer compared to the ones where we were able to achieve a successful reduction. So that is what I wanted to share with you. So I hope I was able to walk you through the motivation for the privacy preservation, which is coming in because all of these assets have multiple stakeholders. And so we do have to, if you are going to have a scenario where, there's a combination of physical attack and a cyber attack, and you really want to be able to leverage assets from non-utility owned entities participate in, say, picking up critical loads or performing a grid service, which might be just voltage control reduction under nominal performance. You need to have a whole infrastructure that basically enables different tools that provides, good prediction first, and then wherever you can, good optimization, and where you can, things of that sort, like grid swing, power swing reduction, and by basically, and of course, duct curve management. So these are all different types of grid services that I hope you were able to see we can manage with these multiple owners participating in the overall exercise. And these algorithms, for instance, PAC, which basically gave us a way of conveying information between each other using and carry out distributed optimization and preserving sensitive information and keeping them private. And also federated learning, where you can do many of these computations in-house, which uses sensitive data. And only at the very end, after you finish training, it's only at the market stage, but basically these IoT networks are bidding in, which hopefully happens through a protected network. And so there is no compromise there, but not for basically when you're trying to learn and train the data and you're not revealing any sensitive information during that stage. And that both of these together represent decision-making tools that allow a judicious and efficient use of IoT networks and power grids. And thank you very much and all of this, I think, are really important for all these assets to come together and realize deep decarbonization in power grids. Thank you very much for your attention, and I'll be very happy to take questions.
Great. Thank you, Professor Anaswamy. It's a really interesting talk. It's great to see that the applications covers from voltage control all the way to power swing reduction, like everything I can imagine. So I have a few questions here. Some
Yes.
are asked in public, some are asked in privately. So the first question, you showed the two similar concept. One is the flattening the dark curve, the other is the power swing reduction. Do you have any definition on how flat is good enough, and what is the power what is a successful power swing reduction? So do you have such kind of definition?
No, in our case, basically, this was our definition, right?
Mhm.
So as far as we were concerned, a grid swing was something that is assumed to occur if your delta P exceeded the 90th percentile. So this, I mean, of course, there is a certain amount of heuristic in here, and it certainly it can be improved. But for our purposes, this was our definition. And essentially, anytime it exceeded this threshold, then that's not a good thing. And so we assumed then that there is some sort of a direct load control that is possible. And so and we assumed that a certain percentage of the loads were flexible, and those loads were curtailed in order to get this performance. So in this particular case, this was our definition. Certainly we can relax it or tighten it depending upon what the goals are in a particular context. Okay. But, whatever the definition is, the method that we are proposing would be, something that is still applicable.
I see. Yeah, thank you. The next question is related to the PAC algorithm. So if there is a communication failure, can the PAC algorithm be robust to them? For example, there are some communication data loss or some bad data. How do you deal with that?
Yeah, absolutely. No, I think it's a very good question. And in fact, in some sense, that's the whole motivation for introducing distributed optimization, right? And so that if there is indeed a packet loss, then the whole centralized algorithm is not held up. We have not done that yet, but we have in other work in our lab looked at robustness to packet loss. And so essentially the way the algorithm would proceed, I mean, maybe I can go directly to that slide and to walk you through what would happen. So the way it would proceed is basically, let's see, so maybe I can show it to you using this one here. So you have these algorithms and you're communicating this information in here, for instance, wherever the communicate step would occur, this particular quantity is what you need to communicate. And so in the event of a power loss, packet loss, sorry, what you would do is to do a zero order hold and basically transmit the previous information. So obviously this will include a certain amount of suboptimality, but our speculation is that because we have these kinds of convergence results where there is a certain amount of exponential convergence, this algorithm would be robust to those packet loss. And so you would converge to within an epsilon neighborhood of this A star. That's what we expect to happen. We haven't done that yet, but the nice thing about it is that this, whatever epsilon degradation would be limited to what is happening within that neighborhood and would not really, as you go further away from the packet loss, the other entities would basically still preserve more precise performance.
Okay, sounds good. So the next question, Max Patterson asked, what modeling software was used? I guess the question is somewhere after the dark curve slides.
Right. So In this particular case, I believe we used MATLAB and Gurobi here, yeah. But in yeah. Yeah.
Okay. Yeah, I hope that answered your question, Max. So the next question, yes, the next question, can you please elaborate more on what neighbor information is required in the PAC algorithm? So what will be the range for the local copy? Yeah.
So it very much is a question of how you have partitioned, right? So all of the steps that correspond to the communication is what the information is that you're exchanging, some of the primal variables and dual variables, and to whom, to basically as determined by that K, right? However you've determined your partition. So for example, in this particular, in the example case that I showed you, right, you would have to exchange information, sorry, let me just go here. In this very, it was a card. So this is a cartoon example, but still, in this particular case, the information that you would exchange are all determined. So for instance, this atom in here, the K would correspond for Y1 and Y2 have to talk to each other. Here, atom 2, Y2 will have to talk to Y3 and Y4, etc. But it's completely a question of how I carry out the partition. And again, we've done a little bit of work, and it's there in this paper as to what the most efficient type of partitioning is. It very much depends on the topology of the network, and there is also a trade-off between, if you increase the amount of partitions, then you increase the amount of coordination constraints, but you might improve the complexity of the computation of each atom. But if you have fewer partitions, then within each partition, you have a lot of complexity because the dimension is higher. So whatever is the correct efficient amount of performance metrics that you want will basically determine the level of communication burden that you have.
I see. Thank you. So I take one last question, and since it's almost 1 hour, and the question is, what kind of privacy issues exist on the user side? Can you please provide more insights? Because some of the students are confused, wondering what kind of problems they can solve.
Sure. Yeah. Sure. So imagine that you have a sort of a home energy network, right? And if you were to send that data and people are able to eavesdrop, then people will have an information of how much energy is being consumed by that house and over what period, etc. And then that's an intrusion into what is happening at the home level. So you don't want to necessarily share data, and that to a large volumes of that from that house over the network to the utility. And so that's the kind of privacy that we're talking about, that we're not sending the actual data, but we're only sending a model of that in the form of